The Bonferroni method is always applicable. The probability calculation that we just did doesn't say anything about how the tests are related to each other. They don't even all have to be about the same research question. If you and a bunch of friends are each doing hypothesis tests and you wanted to make sure that your family-wise error rate was at a certain level, you could apply Bonferroni. It's not always optimal, though. If we did know how the tests were related to each other, we would probably be able to take advantage of that, as we'll see in the next methods, in order to be a little bit less conservative, not use quite so low a p-value cutoff for each test. So Bonferroni gives you an upper bound for the probability that at least one test rejects. So specifying what the method is, again, if you have k hypothesis tests, k is just some number. If the cutoff for one p-value is 0.05, now the cutoff for each of your p-values will be 0.05 divided by k. It's a very simple method to apply. In parallel, if you're making k confidence intervals, if one interval was supposed to have 95 probability, but now you want to have family-wise coverage, each of the k intervals should be a little bit wider. It should be designed to cover the true value with a larger probability. How do you get that probability? Well, say you have 5 tests. So now instead of a 95% probability, you're going to have 1 minus 0.01 probability. So you're going to make your intervals large enough that you'd expect to have 99% coverage for each of them, so that overall you have your 95% coverage. Here's a picture of the intervals that we generated originally for the CFMT example, and then you see the Bonferroni intervals underneath, which are just a little bit wider. And so the idea is that these wider intervals will be a little bit more conservative, and you can see that's true. For example, for the comparison of business to education, before we made any sort of correction, the original interval didn't quite cover 0, so we were rejecting the null there. We were able to just barely say that business was different than education, but perhaps that's just due to chance, because when we make the Bonferroni interval, which is a bit wider, we do cover 0. We say that we do not have enough evidence to show that business is different than education when we make that Bonferroni correction. So the Bonferroni correction is going to make you less likely to say that you're discovering things, which is what we want, because we know that some of those discoveries are false. Here's another method. Now, Fisher's protected least significant difference sounds like a very fancy name, but it turns out to mean do nothing. This is applicable when you're interested in differences between all pairs of group means. So you have a bunch of groups, as we have here, maybe 4 different occupation groups, and you're interested in looking at all the different pairs of them. Turns out that's exactly what we're doing with the CFMT data right now. So here's the main idea. Proceed with the t-tests as usual. But of course, there's a little bit more to it than that. Start out by conducting something called an F-test that we haven't discussed yet. But there's a test called an F-test for the null hypothesis that the means are equal in all of the groups. The means are equal in all of the groups. Just one test to see whether the means are equal in all of the groups. If you fail to reject that null hypothesis, you don't have enough evidence to say that the means aren't the same in all the groups, just stop and say, well, none of the groups are different than any other group. If you do reject the hypothesis that all the group means are equal, then go ahead and do your t-tests or intervals. How does this help? Well, you're protecting yourself from searching around for a paired comparison that appears significant by starting out with this one test that says, I won't even proceed unless it seems like at least one of these groups is different from all the others. And this helps us in terms of the family-wise error rate. Suppose that the null hypothesis of the F-test is true. All the groups do have the same mean. Then if you do the F-test with a 0.05 cutoff, the probability you'll incorrectly reject the null that all the means are equal is 0.05. In other words, the probability, if the null is true, that you'll get to 2b is no bigger than 0.05. And only if you get to 2b do you even do the t-tests. So the F-test has protected us in terms of family-wise error because there's only a 0.05 chance, if this null is true, that we'll even try to find a paired comparison that is significant. So now the probability that one or more paired tests will reject has to be less than 0.05 because the probability we'd even proceed with this is going to be 0.05. Here's another method. Tukey's honest significant difference, or also Tukey-Kramer is a slight variation of this. This is applicable when you're interested in differences between all pairs of group means. which again is the situation we have here, the main idea is to consider the largest difference between any of the two sample means. So if we have 4 different occupations we're looking at, we're going to focus on the pair of them that's most different from each other. If we assume that we have normality within each group, so the CFMT scores are normal within each group, and we assume the variances of the CFMT scores are the same in every group, then if the null hypothesis is true, so all the group means are actually equal, we can calculate what we'd expect to see for the largest paired difference. Again, if we have 4 different occupations and we'd expect them each to have the same mean CFMT score, and that's actually true that the populations have the same CFMT scores on average, then we can come up with a reference distribution for the statistic biggest sample mean in one of the groups minus smallest sample mean in one of the groups. The Tukey method takes advantage of that. So what you need to know about the Tukey method is that it's the most appropriate method when you are comparing all possible pairs of a bunch of groups, because it's derived specifically for that situation. And so the blue lines here are the Tukey lines. You can see they're a little bit more conservative than Bonferroni. Let me say that differently. They're a little bit less conservative than Bonferroni in that you're more likely to see a difference. They're narrower intervals, so the intervals are less likely to include 0. Scheffe's method is appropriate when you're interested in all possible combinations of group means. So something like the mean of 1 minus 2 times the mean of 2 plus 2 times the mean of 3 minus the mean of 4. All different combinations. The main idea is we're going to control the family-wise confidence level for all those possible linear contrasts. Again, I mean something like the mean of 1 minus the 2 times the mean of 2 plus 2 times the mean of 3 minus the mean of 4. So now we're looking at a lot more than all possible pairs, but all the different ways we could write down equations combining those 4 means. This is going to be really conservative because, as you can imagine, there's lots of different equations that use the 4 means that I can think of. So to come up with an interval such that there's a 95% chance that any interval for any of those different combinations of means will cover the true value, I'm going to get really wide intervals, and that's what you see here. Scheffe intervals are typically so wide as to be not so useful.